Okay, good morning folks. Welcome to Dev 311, Practical Developer's Guide to F#. I'm Ivan Tolson. I work for a company called Mindscape based in Wellington. We make developer tools. And today I just want to kind of give you a little bit of an introduction to a new language that's come out of Microsoft fairly recently, give you a bit of a background onto why it's different from some of the languages that you're probably familiar with, and just outline why it might be of interest to you in your real-world development activities. So there's four main areas that I really want to talk about. We'll briefly just give you a sort of one-line introduction to what is F#. Then we'll take a little bit of a tour of some of the core features of the F# language, and also look at how we work with F# and C# together, dividing responsibilities between the languages to use the right tool for the right job. And then just briefly discussion about some considerations, some factors you may want to think about when you're thinking about whether to implement or adopt F# in your environment, in your enterprise. So what is F#? The one-line description is it's a strongly typed functional programming language for .NET. So let's pick that apart just a little bit. What does it mean? Well, strongly typed, that should be pretty familiar to people. So like C# and Visual Basic, it does quite a lot of checking at compile time. Make sure you don't do dumb things like trying to assign a string to an integer variable, things like that. It's for .NET. That means two things. Firstly, it can use .NET libraries. So all those lovely framework libraries, that huge collection of framework libraries, that huge collection of third-party libraries, they're all accessible to F#. You don't have to reinvent the wheel. You can use all of those familiar APIs just as you already use them from C# or Visual Basic. Conversely, it also means that F# is outputting .NET assemblies. When you compile an F# program, you get a .NET assembly out. And that means that C# or Visual Basic can call into that assembly. Once the assembly is compiled, it doesn't matter what language it originally came from. You can use it from any other language. You've got a great deal of language interoperability just built in by virtue of being on .NET. Finally, it's a functional programming language. What does that mean? That's a little bit more enigmatic. In the languages that we're used to on .NET, like C# and Visual Basic, these are object-oriented languages. So the primary organizing principle for your code is objects and classes. You'll bundle a bunch of state up into a class. You'll declare some methods on that class. You will organize your code around kind of your data structures, around your data objects with methods built into them, with that behavior built into them. In F#, in a functional language, the primary organizing principle of your code is not your objects, it's not your data structures, it's your functions. It's things that take inputs and return outputs. It's calculations, processing pipelines. The data structures are actually much more secondary. They're obviously very, very important, but they're not how you organize your code. They're only how you organize your data. F#'s already in use in a variety of domains. Scientific and numerical computing is a traditional area of strength for functional languages. F#'s had a pretty big uptake in the finance arena, so I know there's a lot of banks that are using F#. I think even KiwiBank here in New Zealand is using F# already. Along with that, there's insurance. It's found a little niche in the language development space. It's very easy to build language parsers or domain-specific languages in F#. But it's also a really good general-purpose language. I'm not expecting everyone to leave this talk and suddenly switch over to F# for all of their programming. That's not realistic, and why would you need to? But even for general-purpose programming, even for just writing application logic, it's actually a pretty neat, pretty powerful, pretty concise language. F#'s been around for a few years now. It was available as the first version was available as a free download for Visual Studio 2008. It's now actually included, F#2 is included in VS 2010. It's available out of the box. There is also a free download of F#2 for Visual Studio 2008 for those who aren't able to upgrade. And it runs on all of the major .NET platforms. So it runs on the desktop CLR, it runs on the Silverlight CLR in the browser, it runs on Windows Phone, it even runs on Mono if you're so inclined. So I think that's enough about the background. Best thing to do is probably just to jump in, show you some F# code, and let you get a handle on what it's about, what's different about it. So we'll start with some pretty basic stuff. First thing we're going to want to do is obviously we need to know how to assign variables. So This should be pretty familiar from C#. I don't think there's going to be any surprises there. The one thing that you'll notice is that we're not specifying the types of these variables. We're just saying let num equal, let str equal. And if we hover over that, I hope you can see that F# has actually figured out that num is an integer and that str is a string. So let here is working very much like the var keyword in C#. You're not having to explicitly write out the types of these variables, they're being inferred for you. What may be a little bit more unusual, maybe a little bit more different, is that you also use the let keyword to introduce functions. So in C# or Visual Basic, you've got an entirely separate syntax for creating functions, for creating methods, compared to creating variables. In F#, it's just the let keyword. So for example, here we've got a function that calculates the side of a right-angled triangle. Here we've got a function that checks divisibility of one number by another, obviously very trivial examples. But let's take a look at this in a little bit more detail. Compared to C#, you may think there's a bunch of things missing from that declaration. Firstly, again, there's no types. It doesn't say what x and y are, it doesn't say what the return type of that function is. And yet, if we hover over it, the way that F# formats function types is a little bit weird. Don't worry about that. What that's telling you is that it takes two floating point numbers as input and produces another floating point number as its output. And F# has managed to work that out just from the definition of the function and from the usage of the function elsewhere in the program. So we can already see we're saving quite a bit of typing there just by virtue of not having to enter those explicit, say that these things are doubles. The other thing that you'll notice that's missing is the return keyword. The reason for that is that F# as a functional language, it's all about values. Everything has a value. Everything is an expression. This is in contrast to C# or Visual Basic, where everything is a statement. In an object-oriented language like C# or VB, the lines of code are instructions. They're imperative instructions to the computer. Do this, do that. The return statement says, stop running this function and send this value back. Whereas in a functional language, the function just has a value. The side of the right-angled triangle just is the square root of the sum of the squares. There's no return involved. There's no stop running this. It just has a value. Does that make sense to people? Is that pretty clear what's going on there? Yep. One other little detail that I'll just point out, you'll see there's no braces around that function body the way you might see in C#, or no function end function the way you would in VB. F# handles blocking by indentation, so the fact that that is indented is actually significant. So if you're familiar with the Python language, it's similar to that. The reason for this is basically that if you're writing your code well, you'll be indenting structure anyway. And if you're indenting things anyway, then we don't need the braces anymore. They're just superfluous. The indentation should be enough. And in fact, having braces and indentation can be misleading if the two are out of sync. So let's give this a quick try. Let's actually see some code running. One handy feature that F# has that C# doesn't is this F# interactive window. This is a little window where you can enter F# expressions. You can just type them in and have them evaluated, and it will kind of remember the context. It will remember things like variables. And another little handy trick with this is that you can actually copy code from your program into the interactive window by pressing Alt-Enter. So I'm going to press Alt-Enter now. That's going to open System. And it doesn't actually copy the code into the lower window, but it does execute it there. So if I now do a let in the lower window, you'll see it's created that function, and I can now enter stuff into that window and get things calculated for me. This isn't a substitute for proper testing, for having an automated test suite, but it is pretty handy for that kind of exploratory programming, for trying to figure out interactively what's my function doing, is it returning the right values, is it returning the wrong values. So for a real production program, you're going to want to move that testing into an automated test suite, NUnit or MS Test, whatever, but this is really handy for just sort of exploratory, trying things out. Okay, here's another classic example, the factorial function. Now, again, I want to highlight everything's an expression, everything has a value, and that includes what in C# would be the if statement. In F#, if isn't a statement, it's an expression. It has a value. And therefore, so this is saying that if n is less than 1, then the value is 1, the value of this expression is 1. Otherwise, the value of the expression, the overall expression, is this. Consequence of that is that you can't leave out the else clause, because the expression, whether the condition is true or false, there has to be a value to the expression. You can't have no value. So again, we don't need to return there. We're just getting the value of the if expression is the value of the whole thing. And once again, we can see that working nicely in the interactive window. Unfortunately, our function here has got some limitations to it. If I do that, we get a negative number, which is kind of not really what you want from a factorial function. Why is that? Well, if we look at what's been inferred for fact, it's been inferred as integer to integer. Now, those are 32-bit integers. Those are like your C# int type. And as you'll have found, if you've done multiplication in C#, if you multiply or if you do an operation that takes you beyond the bounds of the int32 range, beyond the maximum value of int32, it will flow around into a negative value. And you'll get bizarre results. And that's exactly what we're seeing here. So what can we do about this? Well, F# supports the idea of big integers. Now, big integers, they're actually part of a numerics library that came in with F#1. It's now been folded into .NET 4. And if we put this little, or so I should say a big I, suffix after a 1, then F# will think, it's like putting an L after a number in C# to say this is a long, or an M to say it's a decimal. This says, I want you to treat this as a big integer. And if we look at fact now, you'll see that's been inferred as being big integer to big integer, rather than normal int32. So if I run that in interactive, and now I can go like that, and now I've got a much more sensible result. In fact, I can deal with some decent-sized numbers. Takes a little while. There we go. So I know you guys are going to want to check this, so we'll just... I hope you're writing this down because there'll be a quiz on this later. Oh. And there we go. So big integers can get pretty darn big. There is no limit to the size of those things. So you can, I'm sure you can imagine, you can see the application of this to sort of scientific and numerical computing. You can probably see the application to finance, where you're dealing with obviously pretty large numbers, particularly, for example, if you're dealing in Zimbabwean currency, then being able to deal with numbers this size is really, really important. Okay. So another difference between F# and C# is that in F# you can define your own infix operator. So in C# you can overload things like plus and times and minus. In F# you can actually add new infix operators. I'm going to show you a very simple example here. This is actually surprisingly powerful. You can create whole sort of mini languages within F# by virtue of defining appropriate infix operators, and you can create a very sort of fluent style of API. I'm not going to do that here. I'm just going to use a very dumb exponentiation operator. The magic is those brackets around the function name. By putting brackets around that, I'm saying I want you to treat this as an infix function rather than a sort of normal prefix function. So again, F# infers the type, and I can now write a rather more natural syntax for exponentiation than I can using math.pow. The last core construct I want to show you, the last primitive construct I want to show you, is something called pattern matching. And I'm going to start with a really trivial example. We'll see some more realistic examples as we go through the demo. Pattern matching, so this is my advanced troll simulator for Terry Pratchett fans. Everyone needs a troll. In this case, we're basically using the pattern matching as a switch, a glorified switch statement. So what is this match keyword? This match keyword is saying, I want to look at the value of this, I want to check it against each of these patterns. And the first one that it matches, I want the thing on the right-hand side of the arrow to be the value of the expression. Now, in this case, n is just an integer. It's been inferred to be an integer because it's being compared with integers. So these patterns are very simple, literal patterns. They're constant patterns, which makes it pretty much exactly like a switch statement in this case. The only note is this final one. That underscore means don't care, anything, any input matches this. So the behavior of this, I think you can probably predict it pretty easily. Is your output. You can also, by the way, have guards in here. So I could say I want to match anything, but only when n is negative. And that will now give us a rather more satisfactory answer when we put in negative numbers. There we go. Does that pattern matching stuff make sense to people so far? It's a very simple example, but is it clear what's going on there? I'm seeing some nodding. I'm worried I'm not seeing enough. Okay, we'll proceed. Excuse me. All right, so we've seen how F# deals with simple primitive values, integers, strings, floating point numbers, that kind of thing. Obviously, in any realistic case, you're going to want to be dealing with composite chunks of data. And F#'s got a number of ways of putting primitive values together into bigger things. We'll just look at some of those now. So the first one that I want to show you is F# lists. You may think you know about lists, and undoubtedly you do know about .NET lists. The F# list is not list of T. It is not the system.collections.generic.list of T. The F# list is more like a linked list, and a crucial thing about it is that the F# list is immutable. With a list of T, you can go in there, you can do add, you can set values at an index, you can remove values from it, and you'll be modifying the list as you go. In F#, you can't do that. The list is immutable. Once you've created the list, it cannot change. The first reaction may be, well, this sounds crazy. Sure, if I need to be able to add things to lists. I need to be able to remove things from lists. You're really saying I can't do that. The answer is, yes, you can do that, but what F# will do is it will give you a new list. Rather than modifying your existing list, it will give you a new list. This is not entirely unfamiliar. So if you think about strings in C# or strings in .NET, when you append something to a string, you don't modify the existing string. You get a new string back, which you can assign to the same variable or a new variable, but you're not modifying the actual string itself. So strings in .NET are immutable, lists in F# are like that. Why does F# do this? Well, there's a number of reasons for that. I guess the first one, the primary one, is probably safety. If you've got a list that is being operated on by multiple threads, and bear in mind, the way that programs are going now, we're getting increasingly multi-threaded. If you want to get performance, you have to be able to distribute across multiple processors. Therefore, if you're sharing a mutable list, a changeable list between multiple processors doing parallel computing, and they're all adding and removing and modifying things at the same time, you have chaos. No thread knows which other thread is doing what at any given time. It doesn't know whether the data is accurate or stale or is in the middle of a transaction or whatever. It's chaos. If you have immutable lists where doing something produces a new list rather than changing the old one, then you've always got that kind of atomic, you've kind of got guaranteed integrity there. Another reason for having lists as being immutable is efficiency. And this may seem strange because you think, well, hang on, surely I'm now making copies of these things all the time rather than just modifying them in place. But actually, when you create a new list, it can actually share resources with other lists. So, for example, when I prepend an element to a list, all F# actually needs to do is create a cell containing that element with a pointer to the existing list. Now, if that were a mutable list, like a list of T, that would not be safe, because some other function later on could come in and modify the list that I'm pointing to, and that would impact my list over here, my joined up list. But because this is immutable, it can never change, it is absolutely safe to combine those two. I'll show you how that works. This is an F# list literal, so square brackets and semicolon separators. And I can now create another list from that by prepending something to it using that double colon notation. So you can see that small primes is now that expanded list. But if I look at small odd primes, you can see that hasn't been changed. And in fact, if I look at there's actually the tail, that is to say everything but the first element of small primes, is actually reference equal to that original list. So that shows us that F# has created that small primes list very efficiently. It hasn't copied the small odd primes list, it's just referenced it, and therefore you've got a very efficient way of building up these lists. You're minimizing use of memory, minimizing your processing time. The final impact of immutability, which is more to do with record types than with lists, but I'll mention it now anyway, is to do with persistence. Now, by persistence, I don't mean that you can save them to disk or whatever. That's not really all that interesting. But the fact that you've got previous versions hanging around. So let's take something like a board game program or simple sort of turn-based game, where you might model the state of the game by a game state record, which have information about things like what the deck of cards, what order is that in, the state of the board, what pieces are in which squares, that sort of thing. Now, if that were a mutable C# object, then when the user took an action, you'd probably just call a method on the game state class, which would modify the internal state of the object. Problem is that's destroyed the previous state. In F# what you would do is you have a game state record, and when the user made an action, you would you would create a new game state based on the old one with the appropriate change. So, for example, you might create a new game state which is identical except for the fact that this piece was now in a different place. Because you're creating a new record in that case, because the old record is not modified, only a new record is created, you still have the old one around. And that means that undo falls out almost for free. If you're mutating an object, if you're destructively changing an existing object, then you have to have some sort of command infrastructure or some sort of history infrastructure to handle undo. With immutable records, with immutable data, that kind of facility falls out pretty much for free. Does that make sense to people? Can you see what's going on in the list world? Okay, let's take a bit more of a look at lists. So F#'s got a bunch of facilities for working with these things. The one I want to highlight is the equivalent of LINQ, I guess. So F#, you can use LINQ directly from within F# if you want to, but F# has actually got some built-in functions that do pretty much the same thing. Use slightly different names for historical reasons, but they should be pretty familiar to you. So, for example, you've got the list.map function, which is pretty similar to the LINQ select function. It maps a function over a list. It applies the function to each member of the list. And of course, it doesn't change the list. It returns a new list with those mapped values. Similarly, you've got, for example, list.filter, which is like the LINQ where operator. It filters the list according to a certain criterion, the things which meet that criterion. And again, returns a new list. You can also see that's the F# lambda syntax. It's pretty similar to the C# or Visual Basic one. Should be no surprises there. It's just a quick way of producing anonymous functions. So if we have a look at that in interactive, I'm sure you can imagine what that's going to do for us. And there you go. Obviously, we know from LINQ that it's very convenient to be able to compose list operations. Come on, mouse. And we can do this in a really ugly way if we really want to. So if I imagine that I want to square the even numbers, then the first thing I've got to do is I've got to filter out, I've got to filter just the even numbers, then I've got to map the square function over those. And that's kind of ugly to do in function, in a sort of strict functional approach, because you've kind of got to go, well, I want to do a list.map. What do I want to map over? I want to map over the results of this filter, and that's got to be applied to my actual argument. This is really bad because you end up having to read the thing in the wrong direction. You're kind of thinking, I want to take my numbers, map them, take my numbers, filter them, map them. But the way that this is written, it's kind of looks like it's doing a map, then a filter. You have to read it from the inside out. And there's all these brackets that make it really hard to read. So F# has this thing called the pipeline operator, which is this little pipe greater than symbol. Pipeline operator is very simple. All it does is it says, I'm going to put the argument before the function I want to apply it to. So it says that instead of going list.filter of nums, I'm going to go nums and pipe that into list.filter. And that means that I can now start to build up a chain of these things to compose them. So nums gets passed into list.filter. The results of that get passed into list.map. I could consider going down to doing an order by or whatever, a sort, and chain for as long as I wanted to. This is kind of like extension methods in C# and Visual Basic. So F# functions are very much like static methods. The reason we don't write LINQ using static methods is because it would look exactly like this. I mean, you could write your LINQ queries with enumerable.select of enumerable.where, but it would just look horrible. The extension method syntax in C# allows you to put that first argument, allows you to move that outside the function and put it at the front before a dot, and then it makes it much easier to compose those functions. The pipeline operator pretty much turns any function into an extension method. You're not using a dot syntax, obviously, but effectively it's doing the same kind of thing. It's allowing you to move an argument to the front and chain things off that. Something I want to call out here is also this shorthand lambda syntax. So if we look at something like this, that's actually got quite a lot of noise to it. I'd like to be able to say I want to filter the ones that are divisible by 2. Divisible by 2 seems to me to be a primary concept. It's a concept that's meaningful in itself. But in C# I have to dress it up with this lambda syntax. In F#, there's this rule that if your lambda is, if the arguments to your lambda, the parameters to your lambda are just the final arguments to the function that you're calling, then you can leave out all of this lambda noise and just write that sort of partially applied function. So that's just a shorthand for funx goes to divisible by 2x. Does that make sense what's going on there? Can you see what's going on with that divisible by 2 thing? The nice thing is that makes it obviously a lot more readable than when you've got all of that lambda noise in there. You might worry that this is going to force you to produce lots of fiddly little functions if you want to take advantage of that, because what if I want things that are not divisible by 2? Do I have to create a not divisible by function in order to take advantage of that shorthand lambda syntax? Turns out you don't, because F# has got a function composition operator, which is this double arrow thing. And that, again, it's kind of a shorthand for a lambda. And it's a shorthand for a lambda which does this and then does that to the result. So again, you can think of this as kind of a data flow thing. F# has actually got 2 composition operators, a left-pointing one and a right-pointing one. In this case, I'm going to use the left-pointing one because that's kind of hinting that the data is flowing in that direction. It's flowing in the direction of the arrow. And in this case, I just think that writing not divisible by 2 is more readable than writing divisible by 2 not going in the other direction. Again, can people see what's going on there? Does that make sense with that, what's happening with that not divisible by 2? Pretty readable? Okay. Obviously, we can define our own higher order functions, these link-like functions that operate on lists that take functions in to be applied or filtered or whatever. I just want to give you, pretty much everything you need is going to be built into F# the way it's built into LINQ. I just want to give you some examples just to illustrate something. Here, for example, is the map, the select function. Here's the filter function. We're just going over the list, checking does it match the predicate. If so, we'll yield that. And this should be pretty familiar from the point of view of if you used iterators in C#. Very similar to that. One thing I want to highlight though is the type inference that's going on here. So when we do say when we create a map function, that can actually work on pretty much anything. There's got to be some compatibility, so we know that the second parameter's got to be a list because we're going to do a for over it. We know that the first thing's got to be a function because we're applying it. We know it's got to be a function from the type of the list because we're applying it to list elements. But look at the fact that I've not had to write any of that stuff. F#, if you can see that little tooltip, F# has inferred that F is a function and that list is a sequence. But it's also inferred that they're generic. That little tick that you can see by the A and the B, bring it into F# Interactive so it may be a little bit clearer. That little tick you can see by the A and the B, that's just F#'s convention for saying this is a generic type parameter. Let's compare that to how you would define my map in C#. So there's the F# signature, and unfortunately I can't actually fit this on the screen because that, no, it's not going to go. That is how big the C# signature is, because you've got to write all of these generic parameters out longhand, list of T result. I'm going to have to specify what the type parameters are, I've got to specify what the kind of the function is, specify the kind of the input. That signature alone is far more verbose than the entire F# implementation. Being able to write these inferred generic types saves so much typing, and select many is even worse. If you can start looking at the fact you're going to have a func of T source to I enumerable of T result, I think that alone is pretty much the same size as the F# signature, and that's just the name, that's just the type of one parameter. So F# is saving us a lot of typing, it's saving us a lot of work just entering all of this boilerplate code. It's working harder, it's figuring things out so we don't have to. The compiler is doing a lot of work that we don't have to do. Does that make sense to people? Yep. Okay. So we talked about pattern matching earlier. We saw a very simple example of pattern matching on numbers. Turns out you can also pattern match on lists. And that's a common way of implementing list functions in F#. So let's consider a try find function. This is a bit like the LINQ first operator or first or default, which just finds the first thing that matches a certain predicate. How are we going to do that? Well, we've got two possible cases. Well, sorry, we've got three possible cases, I guess, when we're going to do a try find in a list. Either we've got an empty list, in which case clearly the element is not in there, because if we're looking for something that matches a predicate in an empty list, there ain't going to be nothing. Yeah? We've got the case where the first thing in the list fulfills the predicate, in which case we've found our answer and we can go home. Yeah? We've got the case where the first thing in the list doesn't fulfill the predicate, but there's some other stuff in the list that might do. We can go and look at that later. In which case, we're just going to call the same, we can request to call the try find function on the remainder of the list. We can get rid of the first one. We know that's not going to match. We're just going to look over the remainder of the list and recursively keep chopping the list down. Does that make sense to people? Pretty simple, just contracting the list bit by bit. It turns out, so with F# pattern matching, we can basically put that very literally into code by writing out those three cases as list pattern matches. This pattern matches the empty list. And in that case, we'll return this none value, which is a F# option. We'll return this none value to say we didn't find anything. This pattern matches the case where there is something in the list. Now that rest part of the pattern might be an empty list. All this is saying is there is something, there is a head to the list, there is a in the list. There might be more stuff or there might not be. There's potentially there's an empty or non-empty list afterwards. We've also got this guard clause on it that says when predicate X. So this is only going to match when there is something in the list and that first something matches the predicate. And in that case we said, that's fantastic, we found our result and we'll return it like that. That's going to be the value of the match expression. That sum, again, is part of the F-sharp option type. It's kind of like a nullable type, where this is the, yes, there is a value, and none is the equivalent of null. It's a little bit more sophisticated than nullable types. We don't really have time to go into it, unfortunately. The final case was where we did have something at the head of the list, but it didn't match the predicate. So that's when it's tried that, but that's failed, so it falls through to this pattern. And in that case, we do a try find on the rest. Can people see how that's translating the rough outline that I gave? So, for example, if I do a try find, if I try to find an even number in small primes, it finds one. If I try to find an even number in small odd primes, then of course it doesn't. You could. So we're looking for kind of a try find, or a filter effectively. You're going to try and find all the results. That's actually pretty much the filter thing. I've used a different syntax there, but you could absolutely do it. Let's just give that a go. So in the case of an empty list, then there's going to be no results coming back from that. If we've got a X rest where it matches, it's going to be try find all rest, and that's going to need to have a predicate in there. So you'd end up with something like that, and if we have a look at that, then you'll see that's taking a predicate and a list and returning a list, which is what we're looking for from a filter. Is that okay? Does that answer the... Yep, okay. All right. So lists are a pretty important data structure, but they don't provide an awful lot of structure to the information that you're dealing with. What happens if you're trying to sort of package up a bit of information together in a class-type record, if you're dealing with a bunch of things that travel together? So let's consider something like a bouncing ball simulation. In a simulation, you're going to take a state, you're going to apply some change to it, and you're going to apply a step function to it, and you'll get a new state of the simulation back. In the case of a bouncing ball, the state is its position, x and y position, and its velocity in the x and y directions. When I'm doing the step function, I'm also going to want to know the force of gravity, and I'm also going to want to know the amount of time that I need to run this step for. So I could model that in a very naive way with this step function that takes in 6 floating point numbers and returns 4 floating point numbers. I think that's a fantastic idea. I can't imagine that anybody would possibly put parameters in the wrong order or anything like that. You reckon? We good with that? No, that's going to be a disaster. Don't worry about the calculations, by the way. That's just to fill out the body of the thing. So, what can I do to encapsulate that a little bit more, to make these things more predictable, to make it less error-prone? Well, one thing I can do is I can bundle these up into a record. And an F-sharp record, it's a bit like a class, but it's very simple to introduce. You just put these squirrely brackets around things, name the fields, name the types. This actually gives rise to a .NET class, and it turns out that once again F-sharp has done a lot of work on our behalf. If I look at that state class, you'll see that not only has it given me the properties, which by the way are read-only because records are immutable, because we like things that are immutable in F-sharp. It's built the constructor for me. So this is disassembling the F-sharp generator code into C-sharp. And it's also given me implementations of the of compare to, equals, and get hash code. So that means that if I want to compare two states, then F-sharp has given me that value comparison already. I don't need to write that out. If I'd written this as a C-sharp class, I'd have had to write my own equals and get hash code methods. Because I'm using F-sharp, I've already got that equality comparison built in, that value comparison built in. So this is now a lot nicer to work with, or at least to have as a part of our API. We can still break it apart easily into the individual bits. You can either use a pattern matching let to do that, or you can just use sort of C-sharp style member notation. But if you look at that signature, the important thing is that's now taking a state and returning a state rather than having 4 independent floating point parameters. This isn't as safe as you might like it to be, though, because, for example, I could very easily make a typo when I'm writing out this complicated gravitational equation, and now that's going to mess everything up. And it would be nice if the compiler could listen to catch that for me. Actually, that's not the ideal example. Suppose that I mix up time and gravity, which I understand Stephen Hawking does on a regular basis. So obviously here I'm multiplying time by time and subtracting that from a velocity, and that just doesn't make sense at all. You know, you can't multiply time by time and apply that as a subtractive velocity. So F-sharp introduces this concept of units of measure, and this is basically just a sort of a qualifier that goes with the number to say what its unit is. You can create your own units. There are some built in as well. So I'm just going to create meters and seconds units. I'm going to create a new type of state which distinguishes between the fact that my x and y are in meters and my velocities are in meters per second. If I now look at building the same function with those things, when I look at that being inferred, F-sharp has actually worked out, I don't know if you can see that, but it's inferred that the gravity has got to be in meters per second squared and the time has got to be in seconds. It's worked out that everything has got to be the right dimensions. And if I now try to make a mess of things like that, then I'll get a compiler error saying, hang on, your units of measure don't match up. So you can see from the point of view of something like scientific computing, or even from the point of view of, say, working with currencies, this is a pretty handy way to avoid avoidable errors, to add a little bit of safety, a little bit of type checking to the compiler, to give you a little bit of additional safety to catch the errors before they hit your tests. This still hasn't got quite there, because if I do something like that, those are still, I'm still multiplying the velocity by a time and adding it to a distance, so that's all still good. From a type point of view, that's still happy. I can actually, ooh, I don't want to do that. There we go. So I can actually go further if I want to. I can define separate horizontal and vertical units, if I so wish, and say, look, now my x positions are in horizontal, my y positions are vertical, and then once again I've got to figure out my speeds are going to be in horizontal and vertical meters per second. And once again, if we look at this, you can see that now it's figured out that gravity goes in a vertical direction, which is good because it wasn't doing that at midnight last night, I can tell you that. And now if I try to put in an incorrect calculation, if I try to use vertical measurements in a horizontal context, I'm going to get compiler errors saying, hang on, your units of measure aren't matching up, something's gone wrong, and that gets caught early. Yes?
You wouldn't be lucky enough to be able to use it on strings by any chance?
Use units of measure on strings? I'd never tried that. I think we should give that a go. I think you can only do it on numeric types or types that are built in numeric types, but let's see what we can do. Let Bob equal... It's not looking ecstatic about that. No, I don't. It looks like I'm not sure exactly why it's producing that error rather than another error, but I think it's in a sense units of measure. You can, I suppose you could use them to kind of generally tag an expression in that way, but they are really designed for that numeric scenario. For example, the fact that units of measure are aware of multiplication and division and addition makes them much more, those are concepts that are relevant to numbers but not really to strings. So it's an interesting idea. Sorry, could you say again? I might be able to do it inside a type. We can try that. No, I'm afraid we don't like that at all. No, it's not happy with that. Okay, so this is an interesting idea. I'd like to move on because we're running a little bit low on time. There's quite a bit to cover, but thanks for those questions. Okay, so now we've got our gravity simulation. We actually want to run that simulation. And although we could kind of write an F-sharp interactive and look at the exciting numbers coming out, I think it's probably a better way of presenting a bouncing ball simulation. And the way I'm going to do that is in Windows Presentation Foundation. Now, F-sharp does not play nicely with WPF. It's pretty much impossible to write a XAML window and have it backed by F-sharp code. But what I can do is I can write my XAML window in C#, and I'll set up a view model for that window. And the main thing I'm going to do is I'm going to set up a timer which ticks every 10 milliseconds and updates the view model. Now, what happens when the view model updates? Well, the view model contains, what does the view model contain? It contains a sequence of steps. So this is one of our F-sharp state objects. Something to notice, by the way, those units of measure have not come across to C#. They're only within F-sharp. They get erased at the language boundary, which is a little bit annoying, but there you go. So we can create one of these. We can create an initial state just by calling the constructor, just as if it were a normal .NET class, because it is a normal .NET class. We can then call this steps function, which I've defined in F-sharp over here. So steps takes an initial state and an interval, and it yields a sequence, or it returns a sequence of that state, and then another sequence that begins at the next state. So I take a state in, I return that immediately, I then calculate the next state and recursively call the function with the next state to produce a sequence of first state, second state, third state, fourth state. This is... Could I detect where it was no longer changing and stop the sequence? You could do, so I could check whether next state equals state using that equality comparison that F-sharp's built for me, and I could break out of that sequence. I'm not sure exactly what the syntax is for that, but yes, I could terminate that sequence at that point. In this case, I'm happy to actually just have an infinite sequence. So in my view model, I'm going to call that steps function, and that's going to return a sequence of states. So on each tick of the main window, I'm going to update my view model. I'm going to go to the next state in that sequence. I'm going to update my view model's X position and Y position. There's just some calculations there just to deal with the fact that we've got different coordinate systems going on. The window size might be changing, things like that. One thing you notice here, why am I doing this little dance with a sequence? Why aren't I just binding directly to the record? And again, it's because the record is immutable. When you're talking about WPF data binding, it's expecting a mutable object that's raising change notifications as it changes. F-sharp doesn't want to do that. You can make it do that if you really have to, but it's not natural to F-sharp. F-sharp is the more natural idiom is to produce a sequence of values, a sequence of things. So to make that, to adapt that to the WPF binding model, we're having to copy each value into the WPF binding model as we go. So let's fire that up and let's actually see the bouncing ball in action, if it's still compiling after all those changes. There we go. And it's a ninja. It's a cuddly ninja, which are always the best sort, but it's a ninja. So you can see that we've managed to call our F# code from C#. We've managed to adapt the F# model into a WPF-friendly model, managed to interoperate those two languages without any real friction whatsoever, I think. It's all just .NET classes as far as C# is concerned. Is it clear to people what's going on there? We've kind of covered a bunch of things. We've covered records, we've covered the producing of sequences, and we've covered the interoperation between C# and F# and the whole data binding thing. Are people happy with how that's hanging together? Are people comfortable with what's going on there? Can you see that sequence of states, how it's being... Yeah, question?
What happens to that infinite sequence of yours once you finish with it?
The infinite sequence, once I finished with it, you're kind of asking how do I dispose of that sequence, really, aren't you, I suppose? Or what's happening in memory? That's a good question. The sequence generator, so this sequence expression, is actually lazy. So if we look at a call stack, we're not recursing down or anything like that. It's actually running that pretty much as a loop. So I think what you probably find is that, yes, you've got a state object lurking around at any given time. But unless you hang on to the old state objects, they become eligible for garbage collection. In this case, we're not hanging on to them, so they will just get garbage collected as it goes. If we wanted to hang on to them, obviously we could have a memory issue, but that's our choice to hang on to those things. If you've got something like disposable state inside a sequence operator, inside a sequence expression, then I think your question, the question of how you clean up is much more relevant. I'm not sure what the answer to that is, but I can have a look into that for you if you can have a chat to me afterwards. But it's very much the same kind of thing as you'd see with a C# iterator where you're using a yield return. For example, what you might do is when that sequence breaks, if you have some way of breaking that sequence, then you could do some cleanup after the sequence exits. Okay. The limitation of records is, of course, that all instances, they've got a single schema. And we know that in reality, you're often going to want to have, you're going to want to have different data shapes depending on different cases. So in C# you typically write a class hierarchy for that. So you define a base class, which might or might not have some state of its own. Then you define subclasses, which would have their own kinds of data. You can do the same thing in F#. It's just an awful lot more concise. So here, for example, is a class hierarchy that represents the result of a calculation that might succeed or might fail. So I'm actually declaring a base class, errorable. I'm declaring a derived class, success. I'm declaring another derived class, error. Again, if we look at that in its C# equivalent, you can see we've got an abstract base class, we've got a whole bunch, we've got all that comparison, equality, get hash code, that's all done for us, and we've got those derived types. There's the error derived type, and there's the success derived type. So you can see there's actually quite a lot of code that's being written for us, but in F# we can write it very, very concisely. How do we operate on that? Well, in C# we would operate on one of the things by writing a virtual function. So, for example, if we want to display it, we'd write a virtual function, the display virtual function, and we'd have different implementations for the error subclass and the success subclass. In F# we can't do that. We can't write virtual members on these simple discriminated unions, as they're called. There's just nowhere to put them. Instead, remember, the organizing principle in a functional language is not objects, it's organizing by functions. So how do we do this? We write a function. It's external to the type, but what it does is it uses pattern matching again to dispatch on the different cases. One thing you'll notice here is, we use the match keyword, and we just name the different cases that we want to deal with. Now notice that we can actually put variable names in there, and those will get bound to the contents of the case at hand. So when this matches the error case, E will get set to the error message, and I can use that extracted error message in my result. Similarly, in the success case, A will get bound to the success value, and I can use that value, whatever type it is, in my success case. And you may think, well, this doesn't seem to give me anything over and above virtual functions. Let's take another example. Let's look at error propagation when we're doing arithmetic. So imagine that we've got errorables of int that are coming from somewhere. We want to be able to add two of these things together and propagate errors through the calculation. So taking two errorables of int and returning another errorable of int. Here now I'm matching two of these things, and I'm interested in if both of them are successful, then I'll get their values and I'll add them. If either of them is an error, then I'll just return that error. Now, can we do this in C# with virtual functions? Turns out not very nicely. So if we imagine that we've got a errorable sum as an abstract virtual function on the base class, then we can implement it for the error case. Here we are in the error case. Implement for the error case very easily. But look at the success case. In the success case, we've firstly got to figure out, is the other one a success or is it an error? So we're already coupling that implementation. We're already having to do some further dispatching within the virtual function. The virtual function alone is not sufficient to dispatch on 2 arguments or 3 arguments or 4 arguments. It only handles 1. So within our errorable sum implementation, we have to actually still be looking at the type of the other thing, the concrete type. The other problem we've got is that what we'd like to, in the success case, we'd like to return this. The problem is that that's only going to work if those values are integers, and there's no way that we can define a virtual function that only works on the integer specialization of this generic. We've got to deal with t's, not with ints. So we'd have to pull this out into a separate function anyway. And F# I think just makes it a little bit easier for us to write that function by virtue of the pattern matching. Okay. We're running low on time. There's one other thing that I want to show you, and that... Sorry? But that wouldn't come with the fact that t has got to be an integer. If I'm writing it as a virtual function, then I can't, because there's no way to say that I only want the errorable sum to exist when t is int. I've got to deal with. I mean, I could change that to being success of t. It would kind of cause other problems, but I still have this problem of what do I do for errorable sum in the case where it's not an int. I want this function to be defined only when t is int. And I can't do that using virtual functions. Okay. So I just want to talk about one little feature of F#, which is kind of handy for certain scenarios if you're doing asynchronous stuff. So again, kind of looking at that, potentially that scientific and numerical stuff where you potentially got some parallel processing, but also for maybe cloud computing scenarios where you're going out to the network. If you're writing C# code, there's 2 ways of going out to the network. You can do it synchronously or asynchronously. If you do it synchronously, then it will block your user interface. So your user interface will freeze. Users will not be able to do anything, even close your application, until the network call returns, which could be many seconds. Not a great user experience. Plus, if you do it asynchronously, you run up against this rather unpleasant API where you have to do everything with callbacks. So, for example, here I'm going to create a web request. I'm going to do a begin get response. I have to give that a callback. When the async response arrives, I can start doing some more logic, and then I can try to do a begin read from that stream, and that's going to have another callback. So you can see that my logic is actually spread across 3 methods there. This simple concept of going out to the web in an asynchronous way, that it's spread across these 3 methods, and it's very hard to follow. It's very hard to see what the sequencing of those is just by looking at the code. F# has a different solution. F# has this async keyword. So basically, if you go async squirrely brackets, then this stuff, everything within those, runs as what they call an asynchronous workflow. Now, Most of this is just normal F-sharps. You can see we've got our usual lets, and this is just a call into a .NET class. But the magic is in this let bang keyword. Inside an asynchronous workflow, let bang means go to the right-hand side, and when the result arrives, assign it to the left-hand side, but yield the thread in the meantime. So this is saying do an async get response, and while that async get response is processing, the thread will be yielded. You'll be able to do other stuff on that thread. Your user interface will respond. But when it returns, at that point it gets assigned to the response variable, and the asynchronous workflow starts again, picks up from where it left off with that now bound, and keeps going. So you can see that that gives us a very top-to-bottom view of the asynchronous workflow. We can see the logic, we can see the processing steps of the async workflow in a top-to-bottom, clear, readable, linear way without messing around with callbacks. And yet it's still actually running asynchronously. Sorry, say again? Why doesn't it make everything asynchronous? Because there is an overhead to asynchrony. The fact that you'd be yielding, so you're saying, for example, why isn't this web request.create, why isn't that asynchronous? Because there's no value to making it asynchronous. That's just something that's happening quickly within the .NET framework. And if we were to try to yield the thread while that was happening, then it would, there's no real benefit to it. It's not taking long enough to block things. In theory, you could make it asynchronous. You create a little async wrapper for those creation things, but it wouldn't really be worth it. That would be nice. I think in an earlier version, they did have something like that, where the behaviour of let would depend. I'm not sure of the details. I think they had some cases where the behaviour of certain keywords would change depending on whether you were in an async workflow or not. But I think it's probably clearer to make it explicit in this way. But yeah, I mean, you're right, it can introduce the sort of possibility of error. If I forgot to put that let bang in there, if I don't let resp equal, then I'd make a bit of a mess of things. Fortunately, again, the type system, I think, would catch me on that. So I did that. Then what is resp? Resp is now an async of web response, which means that I'm now going to get warnings that, hang on, that doesn't make any sense. I need that to be the result of that async operation. So, again, we can test that out from C#. So I've got my view model, and I'm going to have to do a little bit of stuff with dispatches here, but basically I'm going to call this fetch all method, which is an F# method, and that's just going to run over the list of sites I give it, calling this fetch method. There's a bit of verbiage there, don't worry too much about that. The basic thing is we're going to go into this workflow, and no, I'm not going to set a breakpoint there, so we'll just run that up, and it's going to give me a window with the names of 5 sites in it. There we go, let's just maximize that, and I'll do an async fetch from all of those sites, and you can see those are running in parallel. You can see that if I just clear the messages and do that again, you can see my user interface is remaining responsive. Incidentally, the reason why one of those sites is slower than all of the others, I'll give you one guess. Well, I can't find it now. There we go. Can you guess what that is? SharePoint! Hey! It's always slower. I'm sure it's a fantastic product. Okay, so C#5 will be getting a facility very similar to this, probably sometime next year. I don't know exactly when it's going to be coming out. Jeremy Boyd is doing a session on async in C#, I think later today. But even when C# gets this, even if your customers can wait another year before you do an asynchronous operation, F# has still got other async features. Particularly, there's a feature called asynchronous agents or mailbox processors, which allow you essentially to have multiple message processors each running effectively in their own thread, but running their own message processing loops in a very linear way using async workflows, so that you can kind of have parallel processing going on with messages being passed between the different things to interact between them. Don't have time to talk about that, unfortunately. Okay, so that's... Well, actually, I wanted to show lots more stuff, but there we go. So I just want to briefly talk about some considerations for adopting F#. And firstly, I want to talk about the negatives. The three big negatives are, firstly, there's a smaller programmer pool. Fewer people know F#. That means that if you are using F# extensively within your organisation, you'll probably find it hard to replace those people. Project managers will not like this. Project managers love developers to be disposable and interchangeable. And I'm sure we all love that feeling of being disposable and interchangeable. So that's a consideration in terms of continuity, in terms of maintaining applications. The learning curve, to be fair, is non-trivial. I hope I've shown you enough today that you can see the basic shape of F#. You've seen the core operations, you've seen let, match, pipelining, that sort of stuff. On the other hand, it's still got some pretty obscure, hard-to-read corners. I'm pretty sure that : greater than is actually a casting operator. But, I mean, it could be a swear word for all I know. Who can tell? And finally, tooling. F# does not have the same level of tooling as C#. We saw we couldn't really do WPF applications in F#. Similarly, if you're doing, say, Link to SQL or Windows Forms or Entity Framework or Lightspeed or anything that relies on a designer, chances are it will have C# tooling but not F# tooling. This is where language interop helps you out. You can do the bits that work well in C# in C#, bits that work well in F# you can do in F#, and just have the two work together very seamlessly. On the plus side, F# saves work. I hope you've seen that it allows us to write certain constructs, things like discriminated unions, things like generic functions, write them much more concisely, have the compiler do the work for us, generating that code, instead of writing it very verbosely in C#. That ties in with the sort of expressive power of the thing. Things like pattern matching, the option pattern, infix notation, allow you to create these very powerful functions, these very powerful little operators and mini languages within F#. Immutability by default is going to be really important as we go forward into that many-core world when you look at things like parallel processing. And async workflows and agents reinforce that capability to support cloud operations, network operations, and parallel processing of asynchronous activities. And this is a kind of subjective one, but whenever I use F#, it makes me feel smart. It makes me feel like I'm getting something done. When I go back to C# now, I tend to feel like I'm having to write an awful lot of boilerplate code. I feel dumb, I feel constrained. In F#, I feel a lot more empowered, I feel a lot more able. It makes me feel smart, and I really like that feeling. So just to wrap up, a bunch of resources. The Don Syme book is a really good reference. The Thomas Petricek book is, if you want to sort of get an idea of how to apply these idioms in C#, maybe you don't want to use F# itself, but you want to apply some of the same concepts in C#, it will help you compare the two languages and see how they work, how do certain idioms translate between them. It's really good for sort of learning your way around an F# from a C# basis. The book by Giuseppe Maggiore and Giulia Costantini, that only came out like a week or two ago. It's only in ebook format. It's available for Kindle, PDF, and I think the Sony readers. It's about $10. It's a really good read. It's not complete beginner stuff, but it covers the territory really well in a very short format, and it's an absolute bargain. Bunch of blogs on there as well, my blogs, various F# team blogs, and there's some websites where you can try out F# interactively in the browser, and you can get some help, you can get some standard snippets. I think this is a really powerful, interesting language. I think there's a lot of application for it, and for me, it's something which I really enjoy using compared to your traditional C# and Visual Basic environment. And I hope I've convinced you, I hope I've shown you that it's reasonably easy to learn, there's a lot you can do, and it's going to work really hard for you. Thank you very much for your time.